So in this video, we're going to look at implicit differentiation, and we're going to do a work example. We want to find the derivative dy dx for the implicitly defined function x cubed minus xy plus y squared equals cosine y. And typically when I do this myself on paper, I don't actually use dy dx until I get to the end. I use y prime because this is kind of messy. It takes a lot of writing, but I'm going to use it in this example just so that we can be a little clearer about how the derivative is being applied in a couple of cases. But I personally prefer to write y prime as I'm doing the problem out, and then where it applies, and then substituting back dy dx at the end, because again, it's just less writing, but that's a style choice more than anything else. Now, one thing that we kind of have to keep in mind is that essentially the way that implicit differentiation works is by the chain rule. So when you have a function of y by itself, that's really all you're going to do. You don't know what the derivative of y is. You're trying to find an expression for it. But essentially, when you do a function of y, you're treating it like a chain rule. The x terms are going to be done sort of normally, but then any term that has both x and y in it, since we're treating y as if it were a function of x, we're going to have to apply a product rule, or if it's dividing, a quotient rule, and so forth. So it's one thing that we do kind of have to keep in mind as we go, that the interactions between x and y are a thing that we have to concern ourselves with. Now, in our example, essentially what we're going to do is we're going to take the derivative for x of both sides of our equation. So the derivative for x of this side and the derivative of x for this side. And then what I'm going to do here is I'm going to distribute my derivative operator to each term separately, because we know we can do that for derivatives. So I want to take my derivative of x for x cubed, my derivative of x for x times y, my derivative of x for y squared, and my derivative of x for cosine y. Now, some of these are going to be simple, as I said, and some of them will be a little bit more complicated. So the first thing is the derivative for x cubed with respect to x is very easy. It's just 3x squared. Now, for the chain rule portions, the ones where we're taking the derivative of y and there's no other x's, then we take the derivative for the y term, just like we normally would. But then by the chain rule, we also multiply by the derivative for y. So y squared becomes 2y, y prime. And then same thing for cosine y, the derivative is minus sine y times the chain rule, y prime, or dy dx. Now, for the product rule term, for the x times y, we have to apply the product rule here. So the derivative of x with respect to itself is 1. And then we multiply by the derivative, by the y alone. And then the reverse operation, we apply the derivative to y, and then we don't touch x. So, apply the derivative to the first one, not the second one, and then switch it, apply the derivative to the second one, not the first one. That gets us this expression, and then we distribute the minus sign. Now, we're not quite done at this point. We do have to collect all the dy dx terms so that we can say dy dx is equal to some expression that will involve both x and y. So the first operation that we have to do is we have to pull all the terms that have dy dx in them over to the same side of the equation. So I'm going to add x dy dx to this side, and then I'm going to subtract 2y dy dx to this side also. So now this side, the left side, has only terms that do not contain dy dx, and the right side has only terms that do contain the dy dx. And so now we're going to factor out the dy dx so that I have this expression, this parentheses that just in terms of x and y. And then to get the dy dx by itself, I'm going to divide out that parentheses to the other side of the equation. And so that's what I get here. Now, depending on whether you collect your dy dx on this side of the expression, on the right side, or on the left side, that will determine exactly how the signs are here. You could conceivably end up with taking a sign out of the bottom and putting it into the top, for instance. Again, if you collected things on the left side instead of the right side, you would get exactly this expression, except that the sign would be distributed through the top instead of the bottom, or again, or vice versa. Those are the only differences in terms of your procedural work. But because there is still a 1 minus sign, whether it's in the distributed to the top or the bottom, the formula is always going to give you the same answer. And so this is our implicit derivative for dy dx. And because dy dx, the original function is implicit, you can't really solve for y very easily. It may have more than one value at any particular combination. At x may map to more than one y. You need both x and y for the point to be plugged in to obtain the slope at that particular location on the graph. But at this point, the function basically, the derivative formula basically works the same as it would in other problems. If you wanted to find the tangent line, for instance, the slope of the tangent line, the only difference here, as I said, is that you would need both the x and the y coordinates from the point it passes through in order to find the slope. But then everything else would proceed normally.